Good morning, good evening, good afternoon, depending on where you're joining us in the world. Welcome to the MECI Alliance seminar series. My name is Brian, along with Teresa and Irina, we're your hosts for today. But it's our pleasure to introduce Wim van Ries, professor in mechanical engineering. His work is very exciting. He applies advanced numerical simulation techniques to solve bio-inspired problems in fluids and solids and fluid structure interactions. Today, his talk is on high fidelity flow simulations for bio-inspired underwater devices. So folks, please feel free to send your questions in the chat or in the Q&A. We'll hold those to the end. Professor van Ries, thank you for your time today, and I turn it over to you.
Thank you. Thank you for the introduction. Let me go ahead and share my screen. All right, thank you everyone for joining and welcome to my basement. This is where I live these days, and the mess is part of the atmosphere here. So I'm gonna not try to hide it and embrace the situation we're in. I realize it's a kind of an odd day to present, and I hope I can at the very least provide some interesting distraction from everything that's going on in the world, and talk a little bit about the research that I've been doing basically since over the last year and a half or so with my group, since and this is kind of the first main thrust of my research since my faculty position here. And so the talk will be a little bit technical in terms of kind of the numerical methods that we're developing. And I'll show a little bit about the background, what I'm trying to investigate and what we're trying to do. But the details are more on the numerics and the computational side, because we need those pieces to work to be able to accomplish our goals. Okay. So, I'm in the ocean area, okay, and my background is in naval architecture. I studied ship design and ship construction in my undergrad, and so in the ocean, it's a fascinating environment, and there's a ton of challenges right now that we are facing. So these are some examples, right? So we have microplastics threatening the environment, algae blooms, coral bleaching due to the climate change and the temperatures of the oceans rising. And those are things that are kind of on the environmental side that we like to monitor, inspect, and address if possible. On the other side, we have opportunities in the oceans. We have opportunities for offshore aquaculture and kind of addressing some of our food shortage problems in the future. Energy harvesting using floating wind turbines, or even tidal and wave energy, using that source of energy that is the ocean. And just a basic human thing is to explore, right? So finding the 90% of the creatures in the ocean that we don't know yet, okay? And so there's a need for exploring and traversing the oceans using underwater devices, okay? There's also solutions to that. And nature has found a ton of solutions to that. And I put a bunch of keywords here that describe to me what is kind of the essence of the natural solutions. So they rely on soft materials, they rely on actuation, sensing, evolutionary design, learning, and as a consequence, natural solutions can achieve versatility and agility that is unrivaled by man-made devices. Right, so here's a little movie about a school of fish that's being threatened by birds that diving from the free surface, and then there's also larger predators that try to threaten these small fish. And so there's all this collective behavior, adaptivity, sensing, response, adaptivity, all these features of natural solutions that are kind of elusive in engineering devices, right? And I would argue that a large part of that is the sensing, but also the soft materials and the actuation capabilities embedded in these kind of natural structures. And so here's a couple more examples of like the kind of large deformations that fish and swimmers can achieve. The lateral line here on this yellow fish that is the core of the sensing of this fish. And then we know about some of the actuation mechanisms that fish have. So many fish can actuate their fins by actively curving them in response to the flow or in response to their required functionality. And then so this has been known, right? And this has been there for thousands or millions of years. And what is exciting about this current time from the engineering side is that we're getting to the point that we can accomplish some of these things in engineering structures. Okay, and so we can achieve smart and soft structures more and more. We can use additive manufacturing to create complex structures, complex shapes, complex geometries, and we can use optimization and AI to control all these different degrees of freedom in response to a certain sensory perception to achieve our goals. Okay, and so here's some examples of recent kind of engineering solutions. This is an MIT Cecil robotic fish that relies on soft structures to achieve this flapping motion. There's this stingray, engineered stingray from Harvard University, and in a separate line of research, I'm also working on creating structures or designing structures that can achieve large shape deformations, such as this lattice structure that we managed to deform into a human face upon a change in temperature. And so we have this tremendous amount of new kind of degrees of freedom and new structures, and combined with the AI kind of mechanism to learn how to control them. Okay, and so this leads to a design space, and I would argue that simulations, numerical simulations, are perfectly placed to explore the design space from different perspectives. So here's a couple of these features, right? So we have functional design in the center, and then we have kind of the basic geometry kinematics. We have the fluid structure interaction, which is a big part of this problem, is how does the flow interact with the structure, and how does the structure exert forces onto the flow. We have active deformation and control. So when you add actuations, you add another kind of layer of complexity onto this. And then there's the whole kind of closed feedback loop of basically taking sensory perception and driving your actuators to achieve a certain amount of autonomous operation inside this functional design. So we have all these different features of the design space, and different perspectives of tackling the problem, right? So we can study optimality in natural swimmers, find out what are natural swimmers good at, what is the metric that they optimize, why do they optimize that? We can look at kind of the more fundamental fluid mechanics perspective. We can say, okay, what is the relation between form and function? Why does one shape perform better than another shape? And what are the underlying hydrodynamic mechanisms that lead to that? And then abstract from that to kind of think about design rules. Or we can use optimization and AI to just kind of inverse design a whole kind of parameter space inside a whole parameter space and try to learn and optimize devices from scratch for a certain functionality. And so numerical simulations allow you to kind of tackle all these different angles of this problem. And another kind of view of that is that we can look at kind of the more fundamental questions on the left, where we use high fidelity computational solvers for physical analysis, and then to use that to create low order theory or validate low order theory, and also generate data for AI, right? This is kind of a black box form of a low order model. On the applied side, we can also combine the solvers with optimization and learning for optimal design and control. So we have this need to develop high fidelity solvers because we want to know that we resolve the flow correctly. We want to know that we can resolve complex phenomena correctly and efficiently. And then the other part is the robustness, because we want to be able to couple numerical solvers with optimization algorithms, with learning algorithms, and those drive different parameter variations, such as changes in shape or changes in kinematics. And we don't want to go back and implement every change that the optimization algorithm suggests to us by hand. We want the solver to be robust enough that we can just change the parameter, make the flapping frequency different, and we put it in the solver and it goes with it. Right? So we want to have this kind of autonomous or automated design tool. So we need robustness and we need accuracy in a numerical solver. And all of these problems rely on the interaction between the flow and the structure can be typically moving and deforming, right? And so I'll spend a little bit of time talking about what type of numerical solvers exist and what are the different features of those solvers. Okay, and so very broadly, currently, since the last few decades, we have been, dealing with two different techniques in the numerical kind of computational fluid dynamics community. On the left, we have an example of a body fitted mesh. So the yellow object is a body, and then the square is the flow domain. And this body is embedded into the flow. And so you can create a mesh, a discrete representation of the flow, and the mesh adapts to the boundary of the body, okay? So if you do that, you have a very nice feature is that the edges of the boundary always align with, edges of cells in the mesh. So you can easily impose boundary conditions, and you have a very accurate representation of your boundary because you can just evaluate any variable that you want onto on the nodes that coincide with the boundary. And so if you move that, then you have to do some tricks, right? You have to adapt the mesh as the body is moving. And that is non-trivial, but there's a significant effort to make that happen, right? So what you get out of this is accurate near wall solutions. This dynamic mesh adaptation, however, can be expensive. And depending on the shape and the motion, it's not fully automated. It's not robust to arbitrary changes in shape and deformations. And so those two things have provided a drawback to this type of method that for specifically moving and deforming obstacles. On the right, we have immersed boundary methods, and here the geometry is represented independently from the mesh, and it kind of hovers on the mesh. So we have a mesh that is just regular Cartesian squares, and this body is sitting on top of that mesh, and we have to represent the effect of the body on the flow somehow algorithmically rather than geometrically through the mesh itself. And if this mesh is deforming, it doesn't matter if this body is moving and changing and deforming, it doesn't affect the mesh. We can represent that algorithmically onto the flow. And so the mesh generation adaptation is decoupled from the body shape motion, which is a very good thing for robustness. But it's more difficult to create high fidelity solvers, especially when you want very accurate low near wall information, for instance, a pressure on the body wall, right? Or a shear stress on the body wall. This last category, there's two different subcategories here. One is continuous forcing and one is discrete forcing. And I'll talk a little bit about both because I've actually worked with both. And I started out doing continuous forcing, which I'm going to talk about in the next slide. And then we'll move to discrete forcing a little bit later. So continuous forcing IBM is basically a way to represent an immersed boundary in a regular grid. Okay, so here we have the Navier-Stokes equations. And this last term on the right-hand side, this F, represents the effect of the body onto the flow. And if we discretize the Navier-Stokes equation, so F is added on the continuous form. If we discretize it, we smooth that term. So we have to, take a singular term and smear it over a couple of grid points to be able to represent it onto our normal nodes. And so we get this picture on the right where we have the black line, which is the boundary of the body, but we have a region around that boundary that also affects the flow, right? So we have somehow a smooth transition from the flow through this smooth region towards the body, and inside the smooth region, we're slowly, turning up the pressure force, so the forcing term, so that we satisfy the boundary conditions on the body wall. And so as we move this body, this little kind of smooth region is moving along with it, and we have this kind of very simple technique of representing the effect of the body on the flow. So the boundary then is fuzzy rather than sharp. And this makes it challenging to compute, for instance, in this example, the pressure on the wall, because we don't have the sense of a wall in this representation. We just have a region where in the middle the wall lies, but we slowly ramp up from, say flow to solid, right? So it's harder to compute local quantities accurately. The other problem or the other challenge with this method is that the boundary conditions are imposed through a forcing term, which means that we impose them dynamically. But in fact, the boundary conditions are kinematic. They represent a form of, a condition on the velocity. And so if we have to enforce a kinematic boundary condition through a dynamic forcing term, that means we often have to deal with stiff equations or small time steps or complex systems to solve that iterative problem iteratively. And so it's somewhat less efficient to do it like this, but it's very easy to implement and add to existing codes. Okay, so there's a couple of examples here, and I've been working with the penalization method, which is one form of this type of method, and it has allowed us to do a lot of cool things in the past. We were able to take swimmers and optimize them using an evolutionary optimization algorithm, and look at how fish start from scratch, so escape mechanisms of fish, how they start from stationary and get to, you know, an acceleration in a certain amount of time as best as possible. We've been able to do all sorts of optimizations on the shape and the kinematics of fish. And so I put a couple of citations here. And we've been able to couple all of the algorithm with reinforcement learning so that we can do a kind of a follow the leader type of exercise where, you know, the first fish here is swimming along a prescribed trajectory, but the second fish has used reinforcement learning to learn what it needs to do to follow the first one, right? So it's a type of control that is not based on model, but based on a black box reinforcement learning algorithm. And so all of these things are perfectly suited for this method because the method is robust and we can do all these type of arbitrary geometries and kinematics without really affecting, for instance, the mesh, the underlying mesh, right? Because we don't need to worry about the mesh. The effect of the body is incorporated algorithmically. More recently, we've looked at effect of curvature variations on flapping foil proportion. So we're looking at if you take a foil and heave and pitch it in an incoming flow, and then you change the curvature of the foil as you do this. Okay, so you make it curve with the flow or curve against the flow, and what happens to the thrust output or the efficiency. And so we can do the same in 3D and look at the effect of curvature. And we found that curvature can actually increase the thrust production by about 20% and the efficiency by about 15%. So that's ongoing work. So these are some illustrations of this continuous forcing method where we have the forcing term implemented in a kind of a smooth version. So that's all nice, but I've decided to move away from this method. And the reason for that is that I want to achieve higher order accuracy. All these previous results are limited to first order accuracy in time. And that's just not enough to go to kind of more complex high Reynolds number simulations. I want to be able to extract local force distributions, which again, it's difficult to do with this continuous forcing technique because you have a fuzzy boundary rather than a sharp one. And I want to be able to handle kind of large scale engineering type simulations. So 3D high Reynolds numbers, which means I need to incorporate dynamic mesh adaptation, which I'm going to talk about later on, and high performance computing. So I need a new framework besides a new algorithm as well. And so we've been working towards meeting this goal. And the underlying thoughts here is that when we have achieved these goals, we can couple our solver with optimization and AI, which is facilitated by the robustness and the accuracy of the solver. And we can think much broader than just these specific applications, because once we have a more formal kind of discrete forcing approach, we can think about more complex multiphysics applications. So not just fluids, but fluid structures, fluids, so free surface interfaces, fluid acoustic, fluid structure, thermal. There's all these different layers of complexity that are just very difficult to implement with the original continuous forcing technique. And so that's why we've decided to think about a discrete forcing type imposition of the boundary conditions. And then turbulence models is another dimension in this landscape. So let's talk a little bit about this other technique that we've started to implement, the discrete forcing IBM. So we're still thinking about a body that is moving on a regular grid without having the grid adapting to the shape of the body and the deformation of the body. So we start from the regular Navier-Stokes equation here. We have our no-slip boundary on the wall of the body. And when we discretize this, we impose the boundary conditions directly in the discretization scheme. So rather than going on the continuous level and adding a forcing, we go on the discrete level and impose the boundary conditions directly. And so there's different ways of doing that. You can incorporate them in finite difference of weights. You can interpolate near wall cell values to the boundary from the boundaries, and you can cut cells. But the general picture is that you would have this animation on the right here where the intersections between the body and the grid lines are responsible for lead to the imposition of the boundary conditions. So whenever the body changes, we recompute the intersections and we adapt our algorithm near those locations to incorporate the boundary conditions that we need. So in this case, the boundary between the flow and the solid is sharp. And so we can reach higher convergence, both in space and in time, than the continuous forcing. The drawback of this approach is that it takes a significant effort initially, because you have to really go into the nitty-gritty details of your implementation and really adapt the implementation to the boundaries. to the boundary conditions. So there's a couple of examples. The general gist of the method is really as follows. It's really easy to understand in this kind of simple analogy. If we have a simple finite difference algorithm, such as here, and we want to, so a simple one-dimensional case, such as this grid, with a function in blue, we want to compute the first derivative. We know that we can do the standard second order finite difference stencil. If we have a wall that coincides with the boundary and we have a boundary condition imposed on the wall, this FW, we can also incorporate that into a simple second order finite difference scheme. If we have an immersed boundary that sits somewhere between two grid points and we have a boundary condition on that immersed boundary, what we do is essentially equivalent to taking a polynomial interpolation between the wall value and two of the grid point values, evaluating that interpolation on the grid point outside of the wall, and then using a standard finite difference scheme based on the flow nodes and the interpolated values. And you can show that this is the same order of accuracy as everything else. And so this is a very kind of simple way to deal with a boundary algorithmically, and it's consistent and formally the same order as the rest of your finite difference scheme. So in reality, things are a little bit more complex depending on the boundary condition and the dimensionality of the problem. But this is the general idea. So we take that and we combine it with the Navier-Stokes solver. We work with the vorticity velocity form. And so we have the vorticity evolution equations, and the general algorithm consists of two steps. We reconstruct the velocity given the vorticity field, satisfying the no through boundary condition. And then, and there's some details for the connoisseur. And then the flow evolution based on that velocity is just implementing the dynamics of the Navier-Stokes equation. And we have a no-slip boundary condition incorporated through a wall vorticity boundary condition. And this is an algorithm that was developed mostly by people in UC Louvain, some of my collaborators. And this has been our starting point. And so we can show that this works. We can do a test case, which is often used, which is the flow is an impulsively started cylinder in a flow. So we take a cylinder and then just have an impulsive start to it. And we can show convergence in space and time. So we have third order convergence in time, second order in space, which is really beyond many of the techniques that rely on continuous forcing, especially the third order in time. And we can compute forces, right? We can compute forces on the body using basically the local details of the vorticity. And these are maybe some of the not as well-known equations as because most of the community works with velocity pressure, but we can basically take wall vorticity and wall vorticity flux to convert them into a traction force and a pressure gradient, and then integrate those to get global forces. We can also use a control volume approach around the body and look at the momentum balance and analyze the force based on that. But the bottom line is that we can get out of this an accurate measure of the drag coefficient on this cylinder versus time, and also local quantities. So we can get the force distribution and the pressure distribution around the circumference of the cylinder. And so this is really valuable because it means we can take a point on the cylinder and say, okay, I'm going to put a virtual pressure sensor on this point, and I'm going to read off the signal of this pressure sensor and use that as an input for an AI algorithm, right? Or a reinforcement learning algorithm. And so we do need that local boundary information to make that work. And this is what the algorithm provides to us. And that's kind of a standard base case that we often use, but with James Gabbard, who's a graduate student in my group, he's been extending this to different combinations of complexity, right? So we can do multiple bodies. These are the flow past 3 cylinders in a triangle configuration. Periodic arrays of bodies. So this is the flow in a box, but it's really the box represents one element, one unit cell of a periodic array of cylinders in all 2 dimensions around it, right? And so you get all sorts of interesting shear layer instabilities. We can do moving bodies. So this is the flow past the heaving and pitching ellipse. And we can do multiple moving bodies. And so we can take 2 ellipses and have them heave and pitch next to each other. And again, we can take any point on any of these ellipses and just go and evaluate the force at that point, right? And that's really what I'm after, both for the kind of the AI coupling and also for implementing fluid structure interaction later on. Okay, so this is all 2D. this has been a big effort in terms of developing the algorithms together with our collaborators at UC Louvain. And so Thomas Gillis, Philippe Châtelain, and James Gabbard in my group. And we feel like we're in a pretty good place to, think about extending the whole thing to 3D. Okay, and so when you extend this thing to 3D, algorithmically, it's not that much more complicated, but computationally, it gets much more interesting because the extra dimension puts a significant barrier for computational cost, both laminar and turbulent simulations. And so there's typically a couple of ways to try to tackle that. You can adapt the computational resolution to the scales in the flow. So if you remember one of those flowy simulations, you have regions in the domain that are much more intricate than regions in the domain where there's nothing going on. And so you want to adapt your resolution to those regions, right? You then identify them and adapt the mesh. You want to make it scale in parallel. So you want to think about, supercomputers and use hundreds or thousands or tens of thousands of simulations of processors to run 3D simulations with the accuracy that you need. And then you can think about turbulence modeling. So model part of the most expensive features of a turbulent flow to reduce the requirements on the resolution. So I'll talk a little bit about what we're doing on the adaptivity side in 3D, because that's kind of the second major thrust that we've been starting over the last year or so. The strategy that we take for adapting the computational resolution to the scales in the flow is based on a mathematical multi-resolution framework that is based on wavelets. So we're looking at a wavelet-based multi-resolution analysis. And this becomes quite mathematical, but I'll try to summarize it very briefly on a high level in one slide, and then I'll show an example which might be more intuitive. So the goal here is to try to identify for a given signal, let's say a vorticity field or a velocity field, where do I need to refine my mesh? In what regions of the domain do I need to refine my mesh? And in what regions of the domain can I coarsen my mesh and not incur any error of significance? Okay. And so wavelets allow you to do that. They provide this formal basis for judging these refinement and compression criteria. So the basic idea is that you decompose a function space, so L2, into subspaces that are nested. And then for each subspace going from one to the next, you introduce a new subspace, which is orthogonal. And you have basis functions that span each of those spaces. So the space Vj is spanned by the scaling function phi, and the basis Wj is spanned by the wavelet function psi. And so if you do that, and you work through some of the math, you can represent any function in L2 using a decomposition of scaling functions on a given level, capital J, a linear combination of scaling functions multiplied by the scaling coefficients. And then the detail coefficients multiplied by the wavelet functions on all the levels above, okay? And so that is an identity, okay? And so based on the scaling functions and the detail coefficients, the scaling coefficient and detail coefficients, you can reconstruct a function coming from any level, essentially by always adding the difference between going from that level up and then up and then up. And every time you go up, you add the difference through the wavelet functions and the detail coefficients. So here's a little example. Let's take this function. This is a periodic function with a couple of nice, this is like our Wrigley function, right, that we're using for the example here. We have discretized this using 32 points, which are the bars in blue. And we want to do the decomposition of these functions in wavelet space. Okay, so we put the function on the top left here. And we use this identity to compute the wavelet and the scaling coefficients, the lambdas and the gammas. And so on the bottom, we have the scaling coefficients one level down. So we use half the points as we had in the original signal. And then all the differences between that lambda and the actual functions are represented in the detail coefficients on the right, the gammas. And so using the lambdas and the gammas, we can execute that linear sum, that weighted combination of wavelet and scaling functions to reconstruct the original signal. But we can do this again. We can take the lambda on the left here, on the bottom left, and decompose it again into a coarser level and the details, which represent the difference, right? And so now we can reconstruct a function from those coarser details, scaling functions, the lambda 4, plus 2 of the details, right? Because we need one to go one level up, and then we need the second to go to the original function. And you can keep doing that until you're all the way down at essentially one scaling coefficient and a whole bunch of detail coefficients that always allow you to go up in the complexity and go to the original function. And so we implement that, and you can use this to think about scales in the function. So you can think about, okay, if I have my function here, and I do the decomposition, and the details here on the right are always very small compared to the scaling coefficients, then I can safely ignore the finer resolution and represent the function only on the coarser level, right? So I can use the magnitude of the detail coefficients as an indicator for when or where I need to coarsen or refine. And so, that is the basic idea behind this wavelet-based resolution approach that we're taking. And then the fact that it is formal mathematical framework is very nice for a bunch of other features. We can use, we have an explicit error bound. So at any point when you say, I'm going to neglect all the detail coefficients under a certain threshold, we know that the error in the reconstructed function is also bound by that threshold. We can use the wavelets to interpolate and do coarse reconstruction across resolution jumps. And we have this nice kind of dyadic structure of the grid where every time we go coarser, we just coarsen by a factor of 2 in each direction. And so the data structure is based on an octree, and we combine it with block structured grid. And this allows for a very fast, easily parallelizable and efficient way to represent multi-resolution hierarchical grids. The devil is in the details, of course, because when you go to 3 dimensions, things are more complicated. There's different types of wavelets. You have to deal with boundaries, parallel implementation, octree representation, anisotropic domains. But that's kind of the nitty-gritty work that Thomas Chilis is working on a postdoc in my group. But as an example, here's what we get right now. This is a simple simulation. There's not even a PDE underlying. We just take a torus, this ring here, and we just move it through a domain. And the domain has an aspect ratio of 10 in one direction, and then 1 and 1 in the other 2 directions. And then we make the grid adaptively refine around where we have the features of this ring. And this is fully automized, right? So it's based on the wavelets at any step in time. And so as this ring is moving, the grid is adapting around it, right? And we have a pretty high resolution at the finest scale. We have a 1/1024 linear resolution. So every kind of cube here is a 1024 cube if it was refined to the finest level. And from the top, it looks also, you see the refinement kind of following the ring. And what's impressive about this is that we get about, at any point in time, about 15,000 grid blocks here. If we would do uniform across this entire domain, uniform resolution, we would have 20 million grid blocks. And so we use about 0.08% of the computational elements with an error that we explicitly control to be small compared to the fully uniform representation. And this whole procedure doesn't cost very much computationally because it's all regular and structured and based on octrees. So this is where we're trying to get the kind of the bulk of our computational gain when going from 2D to 3D. So really, that's kind of where I'm going to wrap up. I tried to show you a little bit about our steps that we take towards a general interface coupled multi-physics solver. And so we have the 2 ingredients, that immersed interface method, which allows us to go high order implementation of moving deforming interfaces, and then the wavelet-based adaptivity to provide a pathway for the 3D simulations. And combined, I feel like we are ready to break some of the barriers that a lot of the competing IBM techniques are facing. For instance, fast and efficient parallel implementation, turbulence model implementation, and also just general multi-physics coupling beyond fluid structure interaction, like acoustics and multi-phase flow, and all these features that have tremendous relevance, specifically in ocean applications. And so this is kind of the numerical part of the high fidelity flow simulation that I feel like will form a basis for design, optimize, and control of soft, adaptive, autonomous, bio-inspired underwater devices, and much more. We're quite ambitious with this project. So I want to stop there. Stay tuned for the updates. These are some of the acknowledgements. Thomas and James are a postdoc and grad student in my group, respectively. Thomas was in Belgium before with the people on the right here, Philippe and Mathieu, who are in UC Louvain and are my collaborators on the immersed interface method and the multi-resolution parts. And this research was sponsored by the DOE and MathWork for a fellowship for James and Misty to facilitate the collaboration between us and UC Louvain. Thank you all for your attention, and I'm happy to take some more questions. I'll leave you with this video because I like watching this vorticity field.
Wim, very nice. Thank you. I send you the virtual and the physical clapping here. Very good. So participants, please enter your questions in the Q&A, or you can send them directly to me in chat if you don't want to share. But Wim, let me kick it off. I'm very intrigued, and I have way too many questions. I want to give others the chance to ask, but the one I wanted to ask is with respect to non-solid objects, like, how does this apply to things like bubbles that may get, or that may shrink in size or get sort of resorbed, or things that aren't a fixed immersed object?
Oh, so like topology changes.
Yeah.
Yeah. That becomes tricky. I think that becomes tricky in any method that is relying on an explicit representation of a boundary. So, for instance, my ambition with this method is for instance, kind of multi-phase flow applications, is to look at bubbles that do not collapse, or waves that do not break and have all sorts of spray. There exist methods to model that part. So you say, okay, I'm going to take my bubble, and when it shrinks below a certain amount that I cannot represent it anymore, I'm going to replace it with a model, let's say a forcing term or something else. So that's always kind of a way out. But for specific applications that are relying on, spray or bubbles like that are shrinking and collapsing, there exist other methods that do not rely on explicit discretization of the interface that are probably better suited for that.
Okay, very good, thank you. So I'll try to take the questions the order they're coming. The first question is, what computational hardware or servers were used to run the simulations?
Yeah, that's a great question. So the benefit of doing everything in 2D at first is that you can essentially run it on your laptop or a desktop. So all of the 2D simulations were run on simple, normal kind of off-the-shelf hardware it is parallel. The code does use thread-based parallelism. So nothing like MPI, but we use Intel threading building blocks to exploit multi-core nodes. But essentially it's based on 6-8 cores machines. And that's it. The main computational cost here is the Poisson equation that we need to solve every time step, and we use a fast Fourier transform for that. So that's kind of where we spend most of the time. The 3D multi-resolution part was also run on the desktop, actually. So it's quite impressive that we have a domain that would be, I think, 10 to the 10 computational points if it was refined uniformly to the finest level. So 10 billion, and we just run it on the workstation because we are able to adapt the mesh only to where we need it. But that code is designed to work with MPI and distributed memory parallelism. So we're definitely intending that to run on significantly larger architectures, so thousands or tens of thousands of compute cores.
Very good, thank you. A question here is, how did you incorporate the boundary conditions into finite difference weights? And is there any issue encountered during grid adaptation?
Oh yeah, I see the questions. So the boundary conditions are really based on the, oh, I stopped my window here. The boundary conditions are based on the little algorithm that I showed on one of the slides. Oh, I'm not able to get out of this. So let me just share it directly from the slide that I want to show. Okay. So this is really, this slide, I don't know. Yeah, here we go. So this is how we incorporate that boundary on a kind of very rudimentary level, right? So we have this polynomial extrapolation of the field, and we use that boundary condition inside the polynomial stencil to create the polynomial. And then we evaluate it at a grid point so that we can then apply essentially what is the same stencil as in the top left, as if there was no boundary. So we fill in a point on the object side with an extrapolation from the fluid side using that boundary condition. And then once you have done that, you can just apply or find a different stencil as if, you know, you're forgetting about the body. And that's why this is kind of very robust and fast in solving the equations. Any issues encountered in the grid adaptation? So really that simulation at the end is not really a simulation, it's rather a sequence of times that we run the wavelet-based adaptivity on. So we just take this ring and place it at different instances in the domain and then do the wavelet-based adaptivity. There's no sense of dynamics here. And the reason for that is that we don't have, this is you know, fresh off the press. We're not ready yet, hopefully in a couple of weeks but right now we're not ready yet to implement, let's say, a finite difference-based advection scheme into this algorithm. And so we're doing this kind of quasi-steady, right? And so in that sense, there's no dynamics here. It's just a sequence of instances that I wanted to show that I wanted to animate to show that this is at least adaptive and basically automated. We don't need to, you know, give the wavelet-based algorithm the location of the ring, for instance. It will just figure that out on its own.
So two more. Oh, sorry. Go ahead.
Sorry.
I was going. Yep. Go ahead.
Yeah, so there was any issues encountered during grid adaptation. I think we're working on this code. So my postdoc Thomas can probably talk for hours about the issues he's encountering, but I think that goes maybe beyond this Q&A right now.
So two more questions. Let's first one sort of a deep technical one, potentially another one sort of bigger picture. What are the pros and cons of this method in comparison with IB-LBM?
So I guess IB-LBM is inverse boundary lattice Boltzmann method. So there's two aspects of that. One is the inverse boundary, one is the lattice Boltzmann. So I'm probably not comparing finite difference and finite difference kind of discretization of Navier-Stokes with lattice Boltzmann is probably not the right platform here. But the IBM, I think the standard IBM, the kind of continuous forcing IBM, it suffers from a couple of these drawbacks that I mentioned in the beginning. So you have this fuzzy boundary, you have difficulty evaluating local flow quantities, and you have problems incorporating kind of this boundary condition dynamically. So you're ending up doing either iterations to solve what is essentially an elliptic system dynamically, right? Or you're just stuck with small time steps for accuracy. And when you go to sharp interface IBM, I think you're just kind of going on the spectrum between what we're doing and what is continuous forcing IBM. It's probably adjacent to what we're doing, if not identical. So the whole terminology is not that well defined when you go to all the different flavors of IBM. But essentially what I'm saying is talking about discrete forcing versus continuous forcing. And I think that is that would be an accurate assessment.
So the last, thank you for that. The last question is maybe self-serving for you. What would you like people to reach out to you and ask? Hey, I have this cool problem in fish swimming or hydrofoils or sailboat design or underwater vehicles. You know, what do you want people to say? Hey, Wim, can we do this together? What's going to strike your passions to try to answer some of those interesting and fun applications?
Oh, so I think one of the things that I'm always like thinking about in secret is I like to sail. I have done a lot of sailing in the past, and sailing is just such an excellent example of having, you know, sails which deform and flap, and then there's the wind and the water and the waves, and there's all these different features that are coming together between fluid structure interaction and multi-phase flows. So, you know, if when we have all of these pieces in place, then I'm gonna definitely take some time and put my head down and try to work through that. I think for now, we have the 3D functionality is still up and coming. So what we are really, able to run on a production level right now is like 2D simulations with optimization or reinforcement learning embedded in, and that's something that we're really that is kind of ready. The 3D part is always more tricky, and I hope we can, using these multi-resolution techniques, we can kind of bridge the gap from making it kind of one of scientific, high computational cost simulations to being more off the mill kind of prevalent simulations that we can do for many practical applications. So I think part of the problem, or not the challenges in this community of doing the immersed boundary, is that 90% of the people, and including us, we're focusing on kind of low Reynolds number 2D simulations because that is what you can run on a desktop or a small compute cluster. What we're really trying to do is break through that and use the 3D, the multi-resolution, eventually the turbulence modeling to take all of these cool algorithms and make them accessible for more engineering applications. So right now the answer is, anything 2D, we're happy to consider. 3D is give us 6 months or maybe 12 months, depending on the complexity of the problem, and we'd be happy to follow up.
Very good. So thank you for the phenomenal work. I do look forward to the updates and hearing about the progress that you make in 3D and other. So again, thank you for your time today.
Awesome, thank you.
And participants, please join us not next week, because next week is on Wednesday is Veterans Day and MIT is the day off, as we'll take the day off as well. But the following week, November 8th, same time, same channel, sorry, November 18th, we'll be hearing from Dr. G speaking about the impact of COVID-19 on US fuel and electricity demand. So that'll be in 2 weeks. Everybody, please stay safe, take care of yourself, get some relaxation and rest. And while you're relaxing and resting, if you feel inspired to nominate yourself or others to come and speak at a future Mechie Alliance seminar, do drop us a line and we'll work to schedule you probably in the spring, given I think where we stand in the slate for the rest of the semester. Professor Van Rees, again, thank you very much for the great talk and great work. And everybody stay safe and be well.
Thank you so much. Thank you, everyone. I hope you have a great day or evening. Thank you.